Welcome back everyone. In this lecture we will see the first isomorphism theorem and some of its consequences. So let us fix some notations. Let us start with G and G dash being two groups, and we have this group homomorphism from G to G dash. Okay. So recall that some of the notions that we have defined related to this group homomorphism, which is the kernel. So kernel is a normal subgroup in G, and there is this image. The image is actually a subgroup of G dash. Okay. Now what we want to do, so once we know that the kernel is actually a normal subgroup in G, then one can make this quotient G modulo the kernel. Okay. So this is a quotient group or a factor group. So now what we want to do, we want to relate this with the image of G, image of phi. Okay. Indeed what we prove that they are isomorphic. Okay. So let us see how one can prove this. Okay. So and then we will also see some examples of this to understand this better. Okay. So you have a map from G to G dash. Okay. So this is a map. So this map can be actually thought of as a map from G to just the image of phi. Okay. So what is image of phi? This is all the range, all the images of elements of capital G. Okay. So now note that this kernel, okay, let me draw a picture. So this is G, and here you have the image which is sitting inside your G dash. So this is your image. Okay. So note that, so this kernel will be somewhere here. Okay. Where the kernel is mapped to the identity element. Okay. So this entire thing is mapped to this identity element. Okay. So now because kernel is being a subgroup of this capital G, so one can actually talk about the left cosets of the kernel. For example, if we take the left coset of this kernel, so let us call it X kernel phi, and then we want to see where this X kernel phi is mapped. Okay. So let us do this computation aside. So what is X kernel phi? So this is X times Z, where Z is coming from the kernel of phi. So look at all these elements. So let us take some typical element and compute what happens. Phi of XZ is going to be phi X phi Z, but phi Z is what? It is identity because Z is coming from the kernel. So then this is going to give you exactly phi X, and this is true for all Z inside the kernel of phi. So if you look at the image of this particular coset, okay, X kernel phi, because kernel phi is being normal subgroup, this is also same as the right coset kernel phi X. Okay. So where this coset is mapped, exactly to this phi of X. Okay. And similarly, if you start with some element in the image, let us call it A, and then we want to look at what will happen to phi inverse of A. So let us look at phi inverse of A. So what is phi inverse of A? Phi inverse of A by definition all X, okay, in G that are mapped to phi X equal to A. Okay. So let us fix one such X, let us call it X naught, which is inside phi inverse of A. Okay. So then what happens? Then you can see that if you take some other X inside, okay, this is something let us fix. So let some other x inside phi inverse of this A. So then what happens? Then you can see that phi x naught is same as A and then same as phi x. Then if you compute phi x naught x inverse, so then this is exactly equal to, or yeah, phi x naught x inverse. So this is exactly equal to phi of x naught times phi of x inverse. So which is exactly equal to phi of x naught times phi of x inverse, which is A times A inverse, which is identity in G dash. Okay. So that tells you that this x naught x inverse is indeed in the kernel of phi. That means x naught kernel phi is same as x kernel phi. The cosets corresponding to these two are same. Okay. So in particularly you can see that, okay, you can rewrite this as x times x naught inverse inside kernel phi, and then x is inside x naught kernel phi. Okay. So basically if you start with x inside the phi inverse of A, so then you can see that x is inside x naught kernel phi. Okay. So but the calculation, earlier calculation says this pre-image of A is exactly equal to x naught kernel phi. Okay. So if you go back to our diagram, so if you take this A and then look at phi inverse of A, so this is just another coset x naught kernel phi. Okay. So basically what we have done, we have divided this G into these small pieces. Okay. So because like I said, the kernel phi is a subgroup, and with respect to that subgroup, G is union of cosets, because kernel is being normal, left cosets or right cosets, they do not make any difference, they are all equal. But what we indeed observed, each coset is mapped to one single element inside G. So here you have G dash, and here you have G, and this is your kernel phi, and this is some x1 kernel phi, and so on, some xi kernel phi, and so on. So this where this is all mapping, this kernel phi is mapping to identity, and this is mapping to phi of x1 and so on, then this is mapping to xi. Okay. So this indeed tells you that you are partitioning G into smaller cosets, and each coset is mapped to some unique element in G dash or image of G dash, image of phi. Okay. So this already tells you that if you go modulo the kernel, then we must have isomorphism. Okay. So let us verify that. So you have a map from G to image phi, so which is you calling it phi. Okay. So now we are going to define this phi tilde, which is a map from G modulo kernel phi to, okay, maybe I will call it phi bar, from image of phi. So what is this map? You take x kernel phi and then map it to phi of x. So we just verified this map is well defined, because if you take any other element from this the coset, then the image will be same. Okay. That is why this is actually well defined map, and we will directly verify this is actually surjective, injective, as well as group homomorphism. Okay. So the surjectivity is obvious, because any element of image phi will be some phi of x, then you can look at the corresponding x kernel phi that will map to phi of x. So this is obviously surjective. Phi is surjective, is obvious. Okay. Now what's about phi being injective? So look at phi x equal to phi y, then you immediately get phi of xy inverse is exactly identity. So, that will imply that xy inverse inside the kernel of phi. So, that means x kernel phi is same as y kernel phi. So, that is what we wanted to prove injectivity. So, that means phi is injective. Okay. So, now let us verify phi is group homomorphism or phi bar. Okay. So, let me call it phi bar. So, phi bar of x kernel phi times y kernel phi, we want to prove this is exactly equal to phi bar of x kernel phi times phi bar of y kernel phi. Okay. So, let us look at what it is. So, phi bar of x kernel phi is exactly phi of x and phi bar of y kernel phi is exactly phi of y. So, the right hand side is just phi of x times phi of y. What is on the left hand side? You can see that x kernel phi times y kernel phi, because kernel phi is being normal. So, this is exactly xy times kernel phi. So, that means phi of x kernel phi times y kernel phi, okay, is exactly phi of xy kernel phi. So, which is exactly phi xy. But because phi is group homomorphism, phi of xy we have equal to phi x phi y. So, that tells you that phi bar is indeed group homomorphism. Okay. So, we established one group homomorphism which is also isomorphism between these two groups. So, G modulo the kernel must be isomorphic to image. Okay. So, this is something you must have seen in linear algebra. If you have a linear space, okay, let us say T being a linear map from V to W, where both V and W are vector spaces, then we can define what is called the kernel. Kernel of T is those vector V, those are mapped to 0. Okay. But if you think about V, W as groups with respect to the additions that are there in the vector spaces, so then the kernel T is indeed the kernel that we define. Okay. So, in particularly V modulo kernel T as a group, abelian groups isomorphic to this. Okay, let us say this is surjective map. So, then this is isomorphic to W. So, this is something comes for free, but this because V and W possess extra structure, which is there is a scalar multiplication with respect to that, it is actually a vector space. So, this isomorphism is indeed isomorphism of vector spaces. Okay. So, this is very important particular case. So, if we think about it, we have seen many examples. Let us work it out all those examples and then see that what this means in our examples. Okay. For example, we took, so this is the example 1. So, we took G to be R2 plus and then H to be your x axis. Okay. So, that is the geometric example that we saw. So, this is R2 and this is our H. So, now you can ask what is R2 modulo H, because R2 is being abelian group, any subgroup is a normal subgroup. So, R2 modulo H makes sense. So, if you think about it, so we had a map from R2 to this y axis. Okay. So, what is that map? So, that is the projection map, xy goes to just 0 comma y. Okay. So, you take some particular element xy and then project it there. So, this is xy, then you project it to this 0 comma y. So, this is definitely a linear map, in particularly group homomorphism. Okay. So, then what is the kernel of this map? The kernel of this map, let us call it phi. So, this is those xy in R2 such that when you apply phi of xy, that should be 0 in your y axis. Okay, what is y axis is a subgroup, the 0 is just 0 comma 0. So that means 0 comma y should be 0 comma 0, that means y should be 0. So the kernel of phi is exactly x comma 0 in R2 where x is coming from R. But what is this? This is exactly your x axis. Okay, it's easy to see that phi is surjective map. So in particularly R2 modulo H is isomorphic to the image of this phi, which is y axis. Okay, so naturally that is why these lines that we have drawn parallel to x axis, so they naturally parametrized by the y coordinate that is intersecting with the y axis. Okay, so that is indeed gives you the group structure. The addition of these two lines that are parallel to x axis is same as adding two numbers on the y axis. Okay, as groups they are isomorphic. So let us see some more example, okay, somewhat non-trivial examples. Okay, so let us look at C star. Okay, so this is our group. So this is my example 2, and then your subgroup is S1. Again, both are like abelian groups. So S1 is normal in C star. So C star modulo S1 makes sense. Again, this is a geometric example. So you have this punctured plane and you have this unit circle. We already seen that. So any ray is going to be our parametrizing set for the C star modulo S1. So that means the C star modulo S1 should look like this ray. Okay. So let us define a map from C star to R plus, which is 0 comma infinity. What is the map? There is this standard map Z go to the modulus of Z. Okay. So this is my group homomorphism. So now you can easily check that Z goes to mod Z is actually a group homomorphism, because mod ZW is same as mod Z times mod W. Okay. But what is the kernel of this map? The kernel of this map, those Z in C star such that mod Z is just 1, because phi of Z is mod Z and the identity element on the right side is 1. So this is exact. But what is this? This is exactly S1. Okay. That means C star modulo S1 is isomorphic to image of phi, but it is not hard to see, the image is full, it is surjective. So this is exactly isomorphic to 0 comma infinity with respect to addition. But you can see that that is the ray that we are choosing. Okay. For example, if you choose this particular ray, so this is a group with respect to this. Okay. So now let us look at another example. So maybe I will leave this as exercise. You can also look at C star and then modulo, for example, this R plus, which is this 0 infinity, and then check what it is, isomorphic to 1. Okay. So now let us see somewhat interesting example. Okay. So you can also take G to be the set of integers and then H to be the subgroup NZ. Then the G mod H will be naturally isomorphic to the Z modulo NZ that we define. Okay. So that is the motivation for this notation, Z modulo NZ. That means Z modulo NZ is a group that is obtained by going modulo NZ of Z. Okay. So this is something I will leave it again. So again another interesting exercise, you can also try to calculate what will happen to R star modulo plus or minus 1. Okay. So the R star is again punctured line. So this is your R star, and then this 1 minus 1 is there, because all these are abelian groups. So any subgroup is a group. So then what is this? You can see that this will be actually isomorphic to 0 comma infinity. I will actually urge you to look for the homomorphism from R star to 0 comma infinity whose kernel is this plus or minus 1. Okay. Okay, here is somewhat more interesting and again motivated from geometry, some example. Okay. So, we can look at G to be R. As I said, R is abelian, so we can take any subgroup and then look at its quotient. So, let us take H to be Z. Okay. So, then what is R modulo Z? So, like I said, R modulo Z should look like the circle, because you are taking the real line and then you are translating any this interval close to 0 comma 1 with this integral translations. So, that means you can identify, okay. So, this 0 1 with 0 identify with 1. So, this looks like circle. So, that is why you expect this to be isomorphic to S1. So, how it is, how one can prove this? You can take R and then you can define a map from R to S1, take theta and then just send it to 2 pi I theta. Okay. So, then you can see that this kernel of this map, let us call it pi, which is exactly Z. So, in particularly R modulo the kernel pi, which is R modulo Z, will be isomorphic to S1. So, this is obviously onto map and this is a group homomorphism. I will leave it to you to check. So, you get this R modulo Z is S1. So, here is the interesting thing. So, you have this Q mod Z. Okay, this is actually sitting inside R modulo Z, because Q modulo Z is a subgroup. So, this is going to sit naturally inside R modulo Z. So, under this isomorphism you can ask where that will be mapped. We already seen that elements of Q modulo Z, they are all having finite orders. Okay. So, what will be finite order elements in S1? So, finite order elements in S1, they will be just roots of unity. Okay. So, this U, this is the roots of unity. So, that means this is those Z in C such that Z power n is 1 for some n in n. Okay. If you take this as definition of roots of unity, then you can see that Q mod Z mapped by pi to exactly U. Okay. For example, you may wonder, there is this nth root of unity. So, fix n in n, then you can look at all those Z in C such that, or C star, let us put it C star, then Z power n equal to identity. So, this is nth roots of unity. Okay. So, this is nth roots of unity. We have seen that this nth roots of unity is actually a cyclic group. Okay. So, you may ask what will be the pi inverse of un inside this Q modulo Z or R modulo Z. Okay. So, I will leave it to you to find this. Okay. So, find explicitly this pi inverse of un. This is a cyclic group of order n inside Q mod Z. Okay. So, this I leave it as exercise. So, this is kind of opens up so many possibilities. Okay. If you start with any abelian group, any subgroup you can take and then quotient it out and then look for quotient group. So, this is giving us lots of interesting new groups. Okay. So, sometimes we have to be careful. For example, G mod H1 being isomorphic to G mod H2 does not necessarily imply H1 isomorphic to H2. Okay. When you go to the quotient, something very funny thing can happen. Okay. The quotient could be isomorphic, but the original subgroups that you started with may not be isomorphic. So, let me give one example. Okay. So, let us start with G being C star. Okay. So, then you can take H B. Okay. Let us take H, let us call it Hn. So that is your UN. Okay. So C star modulo UN, this is actually isomorphic to C star itself. So how one can see this? So define this map, call it phi n from C star to C star. So what you do, you take Z and then send it to Z power n. Okay, this is naturally a group homomorphism. Then what will be the kernel of this map? The kernel of this map is those Z in C star such that Z power n is 1. So this is exactly UN. That means C star modulo this UN will be isomorphic to image of this phi n. But if you think about it, Z power n equal to W will have always a solution for any W complex number. That means this map is indeed surjective map. So this surjection comes from the fundamental theorem of algebra. That means any polynomial equation over complex number has a solution. So we are looking at this particular polynomial equation, okay, for given W. So that means this is exactly equal to C star. So for all these finite subgroups of C star, if you go modulo C star, you are getting C star. But these subgroups are not definitely isomorphic because they have different cardinalities. Okay, UN has exactly the cardinality n. So when n varies, then they will have different cardinalities. But their quotients, they are all isomorphic. So something very strange can happen when you go to the quotient. Okay. So so maybe I will again give more exercises. For example, you can work it out what will be Q modulo 2Z and then what will be Q modulo even for some MZ for M is being some natural number. Okay, identify these groups. And when I say identify, that means you have to identify this as some known groups which are simple to understand geometrically. Okay. And then, so here is another exercise which is easy. So let G being subgroup of C star, where G is finite. Okay, this is a subgroup. So then you can see that G is isomorphic to some UN, where n is the order of G. Okay, in particularly C star modulo G isomorphic to C star. So for any finite subgroup, you have this C star modulo G is isomorphic to C star. Okay, sometime by knowing some information about the quotient, you will be able to say something about the original group. Okay, for example, you can say that if G modulo the center of G is cyclic, okay, so then G is abelian. Okay, so this is something easy to prove. So you first find out some cyclic generator, use that cyclic generator to prove that G is abelian. Okay, so this is something I will leave it to you. And we also have this lattice isomorphism theorem. Okay, so that is something I already established. So if you have a homomorphism, let's say phi from G to G dash, so we can assume it to be surjective, not a problem, because anyway we are going to restrict to the image. So then we already seen that the collection of subgroups H is a subgroup of G, kernel of phi is contained in H. From this to this, there is a 1-to-1 correspondence from B, which is those H dash, where H dash is a subgroup of G. Okay. So you can see that this correspondence takes subgroup to subgroup. So one can also prove indeed, okay, let me state it as exercise. This also takes normal subgroup to normal subgroup. If n is normal in G, okay, and of course the kernel of phi should be contained in n. So then, Okay, if and only if. Okay, so let me write it properly. Let's start with something in capital A. Okay, this is the hypothesis. So then we have n is normal in G if and only if this phi of G, this phi of n is normal in G dash. Of course, I am assuming phi is surjective map. Surjective map. Okay. In particularly, what one can do, one can look at G modulo n, which makes sense. This is a quotient group because n is normal. What one can prove, this is naturally isomorphic to G dash modulo f of n. And the map is given by a n goes to f of e, sorry, phi of a, phi of n, phi of a times phi of n. Okay. So, this is again immediate from first isomorphism theorem. So, you have to establish a map from G to G dash modulo phi n whose kernel is n. Okay. That is something easy to do. I will leave it to you to check. Okay. So, I will stop now. So, I will continue with second and third isomorphism theorems later, okay, in the next classes. Thank you.